Chapter 1, Exercise 7, 2026. Introduction. Consider real numbers b greater than 1 and y greater than 0. In exercise 1.6, we have constructed a strictly increasing function, x maps to b to the x. The aim of exercise 1.7 is to construct its inverse. For each y greater than 0, there is a unique x in R such that b to the x equals y. Since b to the x equals b to the t, t element of q, t less than or equal to x, it is natural to look for x in R with b to the x equals y in the form supremum w element of real number, b to the w less than y. This idea is realized in exercise 1.7f using estimates from exercise 1.7 a to e. Hints. For a, use induction on n. Use the property b to the x plus y equals b to the x b to the y of the exponential function. For part f, it is important to show that the set A is bounded from above. Solution. A. We prove the inequality b to the n minus 1 greater than or equal to n times b minus 1 using induction on n. If n equals 1, then the inequality turns to equality. B to the n minus 1 equals b minus 1 equals 1 times b minus 1 equals n times b minus 1. Assume that the inequality b to the n minus 1 greater than or equal to n times b minus 1 is proved for n greater than or equal to 1. Then, using the condition b greater than 1, we get b to the n plus 1 minus 1 equals b times b to the power n minus 1 greater than or equal to b times 1 plus n times b minus 1 equals bn times b minus 1 plus b minus 1 equals bn plus 1 times b minus 1 greater than n plus 1 b minus 1. It follows that b to the power n minus 1 greater than or equal to n times b minus 1 for all positive integers n. B. Recall from the solution to exercise 6c that b to the power 1 over n greater than 1. From part A applied to b to the power 1 over n, we have b minus 1 equals b to the power 1 over n to the power n minus 1 greater than or equal to n times b to the power 1 over n minus 1. C. From part B, we have b minus 1 greater than or equal to n times b to the power 1 over n minus 1. Using that n greater than b minus 1 all over t minus 1, we obtain b to the power 1 over n less than or equal to 1 plus b minus 1 over n less than 1 plus b minus 1 times t minus 1 all over b minus 1 equals t. D. From exercise 6, b to the power of x plus y equals b to the power x b to the power y for all reals xy. In particular, b to the minus w equals 1 over b to the w for all real numbers w. Since b to the w less than y, we have that t equals y b to the minus w equals y times 1 over b to the w greater than 1. By part C, there is a positive integer n such that b to the 1 over n less than t. Then, b to the w plus 1 over n equals b to the w b to the 1 over n less than b to the w t equals b to the w y b to the minus w equals y. E. Inequality b to the w greater than y implies b to the minus w less than 1 over y. From part D, there is a positive integer n for which b to the minus w plus 1 over n less than 1 over y. It follows that b to the w minus 1 over n greater than y. F. Take a positive integer n greater than or equal to y over b minus 1. From part A, we get b to the n greater than or equal to 1 plus n times b minus 1 greater than or equal to y plus 1 greater than y. If b to the w less than y, then b to the n greater than b to the w, and b to the n minus w equals b to the n b to the minus w equals b to the n times 1 over b to the w greater than y times 1 over y equals 1. Since b greater than 1, we deduce that n greater than w. In particular, the set A is bounded from above by n, and x equals supremum A exists. Suppose that b to the x less than y, then by part D, there exists a positive integer n such that b to the x plus 1 over n less than y. Consequently, x plus 1 over n element of A and x plus 1 over n less than or equal to supremum of A equaling x. Obtained contradiction proves that b to the power x greater than or equal to y. Assume that b to the x greater than y. From part E, there exists a positive integer n such that b to the x minus 1 over n greater than y. Previous considerations imply that x minus 1 over n must be an upper bound of the set A. In particular, x less than or equal to x minus 1 over n. Obtained contradiction proves that b to the x less than or equal to y. We have proved that b to the x equals y. G. If x less than z, then b to the z equals b to the z minus x plus x equals b to the z minus x times b to the x greater than b to the x, which follows from the inequality b to the z minus x greater than 1. Indeed, there exists a positive integer n such that 1 over n less than z minus x. Recall the Archimedean property of R, Theorem 120a. Then, b to the z minus x greater than or equal to b to the 1 over n greater than 1. We have proved that there can be only one real number x such that b to the x equals y. Comments. Inequality from part A is known as Bernoulli's inequality. Exercise 7 introduces the logarithmic function x maps to log base b of x. B to the log base b of x equals x. This function is inverse to the exponential function. The graphic of log base b of x is a reflection of the graphic of b to the x about the line y equals x. Graphics of functions f of x equals b to the x, blue, and g of x equals log base b of x, red. Comparison to the solution by Roger Cook, DNE. In the proof provided by R. Cook, it is not explained how to find appropriate natural numbers n. F. In the proof provided by R. Cook, it is not explained why supremum A is a real number. Comparison to the solution by Kitwin Yu. G. It is not clear how arguments provided by KWU prove that there is a unique x in R such that b to the x equals y. Our approach gives a direct proof of the needed result. Thanks for watching.